Hey guys, welcome back. So in this lesson, we're going to normalize the three fitness values we got from the previous lesson to a range between 0 and 1. Now, in the beginning of this lesson, I'm going to first show you why we're going to do this and what's the importance of that. And I'm going to use a nice website that draws a graph on the XY plane. So, like I discussed previously in the end of the previous lesson, we have a lot of difference between the magnitude of the different fitness values. So the first one, the view quality, goes in the 100,000 almost. The fitness value for the footprint is more or less between 1,000 and 100, depending. And the shortest distance fitness value has ranges between 0 and 50 more or less. So it's way smaller. So let's go to the website I talked about. And it's really nice because this website allows you to draw a graph on the XY plane, which is very neat. This part is going to have a little bit of math, so bear with me. So first we're going to insert the fitness values, how they are represented on the XY plane. And you need to imagine the XY plane, the x-axis is the gene value. And we're going to assume that when it's 0, it means that the fitness value is at the worst. And when it's 1, the fitness value reaches its maximum, or the optimum, let's say. And the y-axis is the value from the different genomes. So let's insert our first function for the view quality. Now those, as you can remember, were really big numbers. So we need to guess more or less the maximum it can have and also the minimum. So like I mentioned, the maximum is more or less 100,000. So let's use that value. And the minimum value, which is the worst possible outcome, let's say it's 500. So this would be the function 100,000 minus 500 times x plus 500. As you can see, you can barely see the line because it's so steep. So let me go to the graph settings and re-establish the bounds for the y-axis. So let's set it to minus 1,000 to 100,000. So we can see it a little bit more better, and the x-axis to minus 1 to 1, which is fine, I think. So now we have a nice linear function, and if we go to 1, you see that at 1, we exactly reach the 100,000, which would be the most optimum for that function, as we have established. And if it's 0, it's the worst. And we have 500 at 0. So that's nice. So that's the first function, the view quality. Now let's continue with the areas of the footprint. So the maximum they can have is 1,000. And let's say the minimum they can have is 200. We still need to check that, but we're going to get to that later on in the lesson. So as you can see, this line is way less steep than the previous one. And at 1, we reach 1,000, which would be the most perfect outcome, and 0 is 200. Now to get to the third one, which is the distance between the footprints or the building masses. So the maximum it can have, I'm also not quite sure about that. We still need to establish that. We're going to take a look at that a little bit further in the lesson. But let's say 50 would be the most furthest they can get away from themselves, which would be the most optimum. And 0 would be the most worst outcome, which they would stick to each other. And this function, you can barely see it because it's so stuck to the x-axis. But at 0, it's 0, of course, which is the most worst outcome. But if I go to 1, it should hit 50, which it does here. So that's nice. So if I zoom out again to show all three, you see that they affect Galapagos in various degrees because of their different steepnesses of the function. So this is exactly why we need to normalize these three functions. So when they hit 0, the outcome will be 0, and when they hit 1, the outcome will be 1. That's the whole idea of the normalization part I'm going to explain to you. So let's return to Rhino, or Grasshopper, and let's get started. So let me move these panels to the top. Let's first take a look at our view quality fitness value. And we're going to use an expression to normalize that. Now, what do we need? We need the input of the fitness value, which we're going to call A. Then we have the AX, which is the bottom part of the range. And we also need an AY, which is the top part of the range. So the formula we're going to insert is basically going to do the same as this component, the remap number component, which is inserting a value specifying the domain that that value lies within, and the target domain, which is really nice. And we have more or less the same here. It's just that we don't have a target domain, because our target domain is going to be between 0 and 1. We just have the source domain, which is the AX and the AY. I'm using the expression so I can show it to you a little bit more clear instead of the remap numbers component. So this is how the formula looks like. It's the A minus AY divided by the range, and that is AY minus AX. This outcome will remap the numbers we have. So let me insert first a slider that goes all the way to 100,000. Let's say 0 is the most lowest value. Or let's say 500, like we specified in our formula. Nice. So the bottom part is 500, or the bottom range part. And the top one is 100,000. Let me insert a panel. So if my view quality value reaches 100,000, I want this number to be 0. Because we have multiple fitness values, we need to optimize for 0. And as you see, if I go down, you see this value increasing. But if I reach 500, which we said was the lowest, my value reaches 1, which is the most worst case, basically. So what I've done is that all these values in between, I normalize them between 0 and 1. And that's exactly what we want. So let me delete the sliders. Let me connect this one to our view quality value. Now there's just one thing. What is very important is to find the range which these numbers can lie between. And sometimes it's very hard to determine these values, because the view quality fitness values, they depend a lot on the accuracy of the view rays. As you can remember from the previous lesson, we specified a grid of 5 meters for our view rays. But if I make this value smaller, means I have a grid that's more dense, which means that there are more view rays being emitted from the buildings, which means that this value, the view quality fitness value, will be way more higher. So you always need to calibrate these two numbers, basically. Now, and here's where the rangefinder comes into play, which I specified in the beginning. It's a component I quickly wrote, and this component will determine the maximum and the minimum value during a simulation. So that's really handy. And we're going to use this component to establish the bounds. So the way we're going to get the minimum and the maximum of the range is to use a sort list component and flatten the input. So now we have 4 values that are sorted from the smallest to the biggest. Let's get the list item. So we get the first item, which is the smallest one. And then we do reverse, so we get the biggest value. And let's insert them both into the rangefinder. What this component does is that it checks the input value. If it's lower than the previous value, it outputs a new lowest value, and the reverse for the highest value. So it stores the highest value, and when the next iteration comes from Galapagos, if the new value is higher, that will be the new highest value, and if not, it will just pass on, let's say. And the reset button will reset it. So now our lowest and highest value are these two. So let's insert them into the AX and the AY. Nice. So in the next lesson, we're going to continue normalizing the area footprint fitness value and the shortest distance fitness value. And those are going to be a little bit more complex, because with the view quality fitness value, we just want to maximize this number as much as we can. But with the area footprint value, we don't want to maximize this value. We want to optimize it for 1,000 square meters. So if this value gets more than 1,000, we want to penalize it also. So it's a different setup. And the same for the shortest distance, because we're going to specify a minimum distance we want to have, let's say 50 meters. If a value is lower than 15, then I want to start penalizing. But if the value is 15 or more, I just want it to be output at 0. So we need to write a short expression to get to those terms. But we're going to take a look in that in the next lesson. Thank you for watching, and I'll see you in the next lesson.